My name is Samantha Huckabee, and I'm here to introduce to you YFly and the challenge that we accepted for the spring semester of 2017. Our challenge was to create a high-altitude long-endurance glider that would carry a 100-kilogram payload and would fly above Class A airspace or at an altitude greater than 60,000 feet, all while sustaining a flight time of longer than 1 week. In order to meet this challenge, we elected to create an aircraft featuring a high aspect ratio and solar-powered batteries. As far as team structure was concerned, I myself served as team leader with Alice Montague and Jonathan Leeper in charge of CAD and graphics, Blake Baber serving as capture manager, and Tyler Hines as a configurator. For the rest of the team, we split into sub-teams, with Steven Ziske in charge of propulsion and power, assisted by Tyler Hines, Alice Montague, and Blake Baber. For aerodynamics and control, we had Nick Nelson, assisted by Molly Crow and Jenny Weiner. Charlie Johnson took the lead for weights and structures with Jonathan Leeper and Tyler Hines, and for systems, avionics, and ground support, we had Jenny Weiner with Molly Crow and Alice Montague.
The high-altitude, long-endurance aircraft will be required to carry a 100-kilogram laser communication system. This aircraft will allow the communication system to send and receive data over a relatively large terrestrial area. In order to achieve the desired coverage area, the aircraft will need to fly around 60,000 feet. It will be required to utilize a standard runway for takeoff and landing and must be able to sustain a flight time greater than 1 week. The idea driving this concept is its utility as a low-cost option to satellites and the ability to change its operational area as the stakeholders see fit. By incorporating innovative propulsion and design strategies, this aircraft will be able to remain on location without need for scheduled maintenance for up to 400 days. Its low weight and high lift-to-drag ratio will allow this craft to reach its target altitude and cruise with minimum power expenditure.
A detailed aerodynamic analysis was performed to analyze the merits of our high-altitude, long-endurance vehicle design. Our aircraft was required to fly to an altitude of 60,000 feet or higher and cruise there for long extended periods of time, for say over 1 week or more. Now to do this, we really seek to maximize our range and endurance. We chose the FX76MP120 airfoil for this job. This airfoil has a superb lift-over-drag ratio and a perfect 2D lift curve slope of 2 pi per radian. And as you can see to the figure on the right, the flow remains attached for almost the entirety of the chord length and separates right at the trailing edge of the airfoil. In the top right figure, you can see our wing planform design. It has a high aspect ratio of 30.2 in order to reduce the induced drag, as well as maintain high aerodynamic efficiency. Now the wings are washed out at the tips by 4 degrees, which allows the root to stall first, which is a desirable characteristic for stability purposes. There is no sweep on our wing because we're flying at low Mach numbers, approximately 0.16. And the taper ratio of 2 was chosen to just, further decrease the induced drag at the tips of our wing. And a slight dihedral was implemented. It really serves to balance the bending kind of felt by the wing due to its enormous aspect ratio, improve stability, and also give more wiggle room between the ground and the wingtips during landing procedures where the bending might be most prominent. For 3D aerodynamics, we looked at 2 cases, the wing and the whole aircraft itself. For the 3D wing, we conducted a XF-LR5 simulation. As you can see in the figure to the right, the parameters that are outputted show below. So our cruise angle of attack is 4 degrees, with a wingspan of 160 feet and a wing area of 848 feet squared. The aspect ratio, as said before, is 30.2, and we obtained a lift-over-drag ratio of 79.1 for the wing. And this corresponded to a low drag coefficient of 0.013, which is actually almost equivalent to the induced drag coefficient of the entire aircraft itself. Now for the entire aircraft, the max lift obtained is going to be 30.8. And when we actually calculate it using the equations from Brandt et al., our operating lift-over drag ratio was 30.59. So essentially, our aircraft is operating at nearly max efficiency, and so we really couldn't have done any better in that regard.
The plane is fitted with high-efficiency solar panels that are developed by Solero. These solar panels are paper-thin, super flexible, and are incredibly efficient at high altitudes. In 10 hours of sunlight, our solar panels are capable of producing enough power to fly the airplane and charge the batteries for 15 hours of flight time during the night. The batteries on HiLife 3 are lithium-air batteries developed by the University of Tokyo. These batteries have 9 times the power density of current lithium-ion batteries and 7 times that of lithium-sulfur batteries. The 4 electric motors on the HiLife meet all of the thrust and power requirements needed to keep our 2,500-pound plane at altitude. The motor specifications can be seen on the right. The motors are lightweight, incredibly efficient, and small enough to not create a lot of drag. The lifetime of the batteries used on the HiLife 3 is recorded to be 2,000 cycles. Before 2,000 cycles, there are negligible changes in the voltage output. This means that the batteries on the HiLife are capable of lasting around 5 years. If the batteries are producing power at less than ideal rates, they are easily accessible and replaceable. With easy maintenance in mind, the batteries are directly accessible through the use of access panels located along the underwing of the plane for troubleshooting or replacement. To achieve max performance from the batteries, the storage compartments of the batteries will be insulated to ensure that the batteries are in ideal temperature conditions for power output. The power and thrust curves to the right are for cruising at an altitude of 60,000 feet. With a cruise speed of 154 feet per second, the plane is flying close to the minimum amount of power and thrust required to fly at altitude. At 60,000 feet, the plane is able to produce 48 horsepower. This creates enough power to reach a maximum altitude of 70,000 feet. During the day, the plane will fly up to 70,000 feet and then coast down to 60,000 feet during the night to use as little battery power as possible. The blades used on the 4 motors are capable of having an efficiency of 80% at 60,000 feet. With variable pitch props, the propellers are capable of reaching this level of efficiency from all ranges in between 0 feet and 70,000 feet. This high efficiency makes takeoff, landing, and gaining altitude a breeze.
The structure of this aircraft is highly limited by the weight that is provided for the structure of the aircraft. Using the provided textbook examples and charts, and an estimate of roughly 2,500 pounds takeoff weight, the structure of the aircraft is limited to about 1,800 pounds. Or 2,000 pounds. We are currently at 1,800 pounds, which puts us underweight, which allows us to carry a little bit extra in batteries and solar panels, which is a huge benefit for us. The other aspect is that our structure doesn't have to support anything extra, no other materials and stuff. It only has to support the mission payload and no other changing loads such as water or fuel. Part of the design went through material selection, a sketch of where the materials would go, and also where and what lane we would use. The material we selected for the major structural components of the aircraft is aluminum 7-75 Tempera 6. It's commonly used in a lot of aircraft. It's a very high strength aluminum, foreign aluminum, while also having a great strength to weight ratio. The downside of it is it doesn't show signs of fatigue very well, so inspections of the material have to be done very regularly and very carefully and thoroughly. The other materials are steel tin 20, mainly used for its easy machinability and other properties such as that. The last 2 materials are carbon fiber composite, used for its higher strength in conjunction with the honeycomb, giving it a much higher strength in our tips and other portions of the wing. The fiberglass composite is used for our skin, just for its extremely lightweight and ability to be smoothed out quite easily. The structural layout is pretty generic and standard. We have a general T shape of aluminum, providing the major shape of the aircraft. The wings are partially fiberglass and partially composite. The engines need to be supported by the aluminum because they're heavier. The rest of the wing does not, so they can use a lighter material and don't have to have a full aluminum beam going through them. The wheels and landing gear and such are of course made out of steel to be able to support the entire 2,500 pounds of the aircraft. Also, the front landing gear is holding 94% of the weight, and the tail dragger is holding that other 6%. This allows for the aircraft to be picked up by the tail by 5 to 6 humans and moved around if need be.
This portion of our video will include systems and avionics. The component layout in the top picture will show the placement of each component, as well as the center of gravity, which is going to be affected mostly by the 100 kilogram payload, which will give us a center of gravity of about 18 feet. And we placed our components within the system according to our center of gravity of where we wanted our payload. As stated before, the payload design is going to be our greatest factor in this. At 100 kilograms and a 5-foot diameter, which will reach all the way across the fuselage, so the computers will be next to the payload, and the servos and antennas will be further back. The picture below is going to be the interaction of the components. The top row will be when ground support is controlling it, the middle row will be on autopilot. So laser communications will be able to connect to the camera on the plane, then an encrypted storage system will allow the plane not to be hijacked by anybody and only controlled by the user, which will be connected to the mission computer, which will move the servos and flaps and landing gear when it's controlled by ground support. On autopilot, the instruments will have their readings sent to a system on a chip, which will be connected to single boards computers, which will be able to control the servos, which again move the flaps and landing gear. And we will also have a transponder and an antenna that can connect to towers nearby. As well as a transponder, we've included position lights and a beacon to climb and descend through regulated airspace according to FAA regulations for takeoff and landing.